Hey guys, and welcome to our series on sorting algorithms in Python. So in this video, we'll take a look at the QuickSort algorithm. The goal of today's video is to actually help you visualize and understand how the QuickSort algorithm works, and we'll also explain the code required for it. So we've basically divided the video into two parts. The first part takes you through a step-by-step worked example of the QuickSort algorithm. We'll basically show you step-by-step how the QuickSort algorithm actually sorts a list of numbers. All right. In the second part of the code, we'll actually discuss and explain the code required for it line by line. All right. We'll then round up by briefly discussing a few things about the QuickSort algorithm, its time complexity, its big O notation, its best case, worst case, ways of improving it, and how it compares to other sorting algorithms. All right. So before we actually begin, I want to briefly explain a few things about the QuickSort algorithm. So the methodology of the QuickSort algorithm is to first pick a pivot point in the array. Now this can be done in a variety of ways, but a very simple way of doing it is just picking the first element in the array. So in this case with these 8 numbers over here, the pivot point would be 4, all right? Now the next step is to basically divide the array around this pivot point, and we divide it in such a way that 1/2 is smaller than the pivot. All right, that 1/2 of the array, all of the values in it are going to be smaller than the pivot, and the other half of the array, all the values in it are going to be larger than the pivot. So that's what we do. All right, and we achieved this by basically using two indexes. The first index I begins from the 0th index, and the second index j begins from the last index, which in this case is 7. All right. Remember that there are 8 numbers in here, but the last index is going to be 7. All right, because indexing starts from 0. So basically, number minus 1. So this is the first number, so you minus it by 1 to get the 0th index. Okay, remember that. So let's actually begin. So in this this diagram here, I have the pivot marked by red, all right, 4, because it's the first value in the array. And over here I have the values, or actually the indexes of I and j marked with arrows. So I is currently pointing at 4 and j is currently pointing at 6, okay? All right, now listen very carefully to this part. The I index is in charge of iterating through the array and until it finds a value that is greater than the pivot, okay? And in this case, the value of the pivot is 4. So it'll keep iterating through the array, incrementing itself until it finds a value greater than 4. Now, j over here is responsible for decrementing itself until it finds a value that is less than or equal to the pivot. With this in mind, let's continue to the next step. All right, now look at this. Once I completed its iterations, it stopped at the value 8. And why? Because 8 is larger than 4. So it's found 8, it compared it to 4. Actually, it compared it to the value at the pivot, all right, the pivot index. And then it saw, okay, this is larger than the pivot, so I'll stop here. And for j over here, it kept decrementing itself until it reached 3. Then it saw, okay, 3 is less than 4, so I'll stop here. Okay, I've highlighted these two with blue. Now what we're going to do is swap both of these values. One more thing to keep in mind here is that we only swap if the value of I is less than the value of j. All right, if the value of j was less than the value of I, then that means that we're going to be doing something else, all right? That means that there's another problem, okay? So yeah, let's move on to the next step. And here I've shown that the value of 8 and 3 have now been swapped. 8 is now over here, and 3 is now in 8's position. So now we're going to re-continue with the iterations, okay? All right, so the next stopping point for I was 9. And of course, that's because it's greater than 4. And the next stopping point for j was 1. Again, that's less than 4. So good. Now we're going to be swapping both of these values. All right, now look at that. 9, 8, 7, 6 are over here, and 4, 3, 1, 2 are over here. Now, have you perhaps noticed something already? Well, let me point it out for you. You see, the first half of the array, these four numbers over here, are all equal to or less than the pivot, all right? And all the values over here on this part of the array, the second part, are all larger than the pivot. Now, again, that's pretty interesting, right? This is actually the first part of the working of the QuickSort code. All right, next step. Okay, what happened here? Well, the thing is that I continued to go on forward and it stopped at the value 8. And j continued to decrement itself until it found 2. So y8 and y2, 8 is larger than 4, all right, and 2 is less than 4. That's why they stopped here. But we're not going to swap these two. Why? It's because the value of I is greater than the value of j. I mentioned this before, all right, we don't swap unless the value of I is less than the value of j, all right? So this is where the second condition activates, where instead of swapping I and j, we swap j and the pivot. So in this case, we swap 2 with 4, and we get this. 4 is now roughly in the middle, and 2 is over there. All right, so notice something now. This is actually where the first step of the sorting algorithm, QuickSort, completes. Now, everything on the left side of the array is either equal to or less than the pivot. Everything on the right side of the array, 9, 8, 7, 6, are all larger than the pivot, all right? This is the partitioning part of the sorting algorithm, QuickSort, all right? So what we're now going to do is recursively call the QuickSort algorithm on each half of this array. So 2, 3, 1, that's one half, and 9, 8, 7, 6, that's the other half. So we're basically going to call the QuickSort algorithm on each half. This takes us to the next step. All right, this is it. Now look, the reality is that we don't actually create a new array with just 2, 3, 1 and then pass it into the QuickSort function. We don't do that. What we actually do is pass the same array into the function, but we just change the low and high values, which is basically the I and j values. Instead of assigning j the seventh index, what we do is assign j the second index. So we're basically narrowing the search range to just 1. So in reality, the entire array is actually getting passed, okay? The two recursive calls that we make, we're actually passing the whole array into them. But we're just manipulating the values of I and j to ensure that the search range is only on that half of the array that we want to be sorted, okay? So now we have 2, 3, 1 over here. I'm actually starting with the first half of the array. Then once we do this, I'll basically move on to the next half of the array. Okay, so I is 0 and j is 2. So let's begin actually doing the iterations for I and j. So this takes us over here. J didn't go past 1 because it's less than 2. Okay, so it fulfilled the conditions and it stopped right there. I found 3 over here, which is larger than 2. So both conditions have been fulfilled, and now a swap will occur. Okay. Now, this is what the current scenario is. The value of I is greater than the value of j. So if you remember what we did previously, we basically now have to swap the values of j and the pivot. So this is what we end up with, 1, 2, and 3. And what do you know, that's sorted. Alright, so the next step is to actually make the recursive calls. Because remember, we don't just make the recursive calls once, we keep making them over and over again. The stopping condition for the recursive calls is once there's only one element in the array that is being called. Alright, and this is actually this point right here. We're going to call the QuickSort algorithm on 1 and the QuickSort algorithm on 3. And this is actually where it stops. It'll actually detect that only one element is being passed to me. So it'll stop right there, okay? Because there's no point in just calling the sorting algorithm on just one element, because by default, an array with just one value is a sorted array. Remember this. So let's move on. Alright, this is the second half of the array. Now, the value of I is 4 and the value of j is 7. Remember how I mentioned that we're actually passing in the whole array? Well, we actually are, but instead of I is equal to 0, we've done I is equal to 4. This basically causes I to begin from 9. So we're basically ignoring all the values before 9. And of course, the pivot is always the first value in the search range. So in this case, the pivot is 9. Okay, it's marked by red. So let's continue iterating as usual. I will iterate until it finds a value greater than the pivot, and j will iterate until it finds a value less than the pivot. All right? So let's go. All right, now look at this. We've ended up at a very interesting scenario over here. This part is actually going to be filled with several unique cases. So pay attention. I and j both point to the same value. Now, why is this? Well, j is pointing to 6 because it's less than 9, so it didn't move past its initial value. But why is I pointing to 6? Well, the thing is, I is supposed to stop underneath two circumstances. The first is if it finds a value that is greater than the pivot. But the thing is, there is no value greater than the pivot over here. If we were to leave I like this, it would continue incrementing itself and it would eventually go off the array. It would actually increment itself to like 8 or 9 or 10, and that's not even in the array, and that would cause an error. So we actually add a second condition that if I is less than the last index, all right? In this case, the last index is 7. So basically, I will stop at 7 because it can't go any further. So that's why I is actually currently sitting over here. And guess what? The special condition has now activated because the value of I is no longer less than j. Even if it's equal to j, we actually do the pivot swap. So now we're going to swap j with the pivot. We're going to swap 6 and 9. All right? And here we go. 6 is now over there and 9 is over here now. Okay, so what is the next step? Well, the recursive calls are actually the next step. So the problem is over here is that we only have one side. Think about it. 9 is the pivot, but we only have 6, 8, and 7 over here as the left side of the array. There isn't anything on the right side. Well, there's actually no need to worry. We're just going to make the recursive call on the left side. There's no need to worry about the right side. Okay? So let's begin. Here we go. We now have 6, 8, and 7 over here. I is equal to 4 and j is equal to 6. Okay? Now let's actually begin the iterations. Okay. Now look at this over here. J actually kept on going until it hit the pivot. Okay? Because remember, j's condition is to find something that is less than or equal to the pivot. Okay? And I, on the other hand, is in charge of finding one greater than the pivot, so it stopped at 8. All right? When I is greater than j, we swap j and the pivot. Remember? Over here we have a slightly interesting case where j itself is the pivot. See, j is pointing to 6 and 6 is the pivot. We're not going to do anything special. We'll just swap j with itself. So basically, what I'm trying to say is that 6 remains at its position. All right? It doesn't change its position. And we're going to make the recursive calls now. There's nothing on the left side, so we'll just make the recursive call on the right side, with 8 and 7 over here. And this brings us over here, where 8 is now the pivot and 7 is the value, only value that remains besides the pivot. I points to 5 and j points to 6. All right. And here we'll do what we always do. I will move forward to 7, but since 7 is not greater than j, here we'll do what we always do. I will move on till it reaches 7 over here. It won't find a value greater than 8, so it'll just stop right there. J will stop at 7 because it's less than the pivot. And then because I and j are both equal to each other, we'll then swap the two of them to give us this result. And now we have a fully sorted array with us. All right. So we're now done with the first half of this video. And now we can move on to the code section. If you still have some doubts and maybe you haven't been able to fully understand how this works, just wait now, because we'll do another review of the entire algorithm within the code. So if something didn't make sense, it'll probably make sense in the code section. Okay, so here's the code for the quicksort algorithm. We'll begin over here where we have the quicksort function. I pass the array into it, and then I pass the low and high indexes. Low is the first index and high is the last index. Okay, since there are 8 numbers over here, the last index is obviously 7. Now right at the start here, we have a condition if low is less than high. Now this is basically used to detect any scenarios where only one element is passed as the array, as the search range. Because if there's only one value, both low and high will be pointing to the same index. So they'll have the same value. And if that happens over here, we'll just directly return the array. Okay? But if low is less than high, then we'll continue on as normal. Alright? So over here we have the initializations. Pivot is equal to low because pivot is always the first value. Then we have I is equal to low and j is equal to high, obviously. And then here we have a while loop. This is that while loop that's responsible for handling the iterations. It maintains the iterations. It keeps executing them while I is less than j. Okay. Once I becomes greater than j or is equal to j, we basically break out of this while loop, and then we swap the pivot, and then we make the recursive calls. All right. So over here are the 2 while loops which are in charge of iterating I and j respectively. Over here we can see that while the value at I is less than or equal to the value at the pivot, keep incrementing I. So basically I is only stopped from incrementing once it reaches a value that is greater than the pivot. Okay, this is exactly what I told you before. And of course we have this condition over here which prevents I from going out of the array. Okay. And right over here, we have the j while loop, which continues iterating, which continues decrementing itself until it encounters a value that is equal to or less than the pivot. Okay? And then finally, of course, just like how I mentioned earlier, if I is less than j, then go ahead and swap I and j. Okay? And if in this case at least, if I was less than j, we would do the swap, and then we would continue. Okay, we would continue iterating due to this while loop. Okay, because I is currently less than j. But on the other hand, if I was equal to j or greater than j, we would break out of this while loop and then swap j and the pivot. Okay, and then of course we would make the recursive calls. This step only happens once the array has been partitioned into 2 halves around the pivot. Okay. So this is like the partitioning code, and you'll see in a lot of places that they actually put this code in a separate function called partition, but I prefer to keep it all in one function. Alright, so over here actually let's take a look at these recursive calls over here. Now the first recursive call happens on the first half, right? So we basically give it the indexes to basically define the search range. We're still passing in the entire array. See, we're not actually just passing in the a few elements. We're passing in the whole array. We're just manipulating the low and high values. Over here, by this point actually, the value of j, the index of j, is actually the same as the pivot index. So basically what we're doing here, we're saying is that begin from low, okay, begin from the start of the array, begin from the start of the search range, and continue on. The upper limit of the search range is going to be the value before the pivot. And in this one, we're saying that the search range will start one value after the pivot and continue on till the end of the array. Okay? And once these recursive calls are done, and once the nested recursive calls occur again and again, and all this code executes again and again, we then return the final sorted array back here. So let's go ahead and run this. And here we go, our sorted array. Okay. So with this, we're actually done with the video. There are a few more things I want to discuss about the QuickSort algorithm, but I'm going to have to leave most of that for the next video because we're a bit short on time. So for now, I'll just mention this, that the time complexity or the big O notation of the QuickSort is n log n. So that means it's better than any algorithm with the n squared time complexity, all right? So just keep that in mind for now. In the next video, actually, there'll actually be a sequel to this video for the QuickSort algorithm where we discuss its use cases, we discuss how to actually improve upon it, we'll discuss the concept of the randomized pivot, and we'll also compare it to a few other algorithms and discuss its best case and worst case scenario. Alright, so I really recommend you check that out. It's not an official part of the sorting algorithm series. It's actually an independent video that you'll find the link to in the description below. Alright, so be sure to check it out. So yeah, that's enough for now, and subscribe if you want to see more, and I'll see you in the next video.